So let us resume our this afternoon session. It is my pleasure to invite next speaker, Professor Sayar Karmakar. So he is from University of Florida. He will be talking about ARCH-GARCH model, estimation, inference, and forecasting. Okay, so so Sayar, are you ready with your slides?
Yes, I am. I will then share the screen.
Yes, we can hear you.
Okay.
Yes, we can see the screen also.
Okay, perfect. Thank you. Yeah, I'll then take over now. Thank you for the introduction, and thank you, Digantada Rituparnadi, for the kind invitation to talk here. So today I'll be talking about, this is a very broad topic. So unlike the previous talk, this one will be sort of an amalgamation. So these ARCH-GARCH models have been pretty popular for last 40 years. Like ARCH was incepted around 1982. I will tell a little bit of story. And then GARCH was invented around like 4 years after the 1986. But after that, there's been quite a bit of work in the area of time series and financial econometrics. People regularly use these models. So this talk will be kind of an amalgamation of a few works that I have done around these models. So I will initially just give like or build some motivation for this type of models. Then I'll talk about some time varying like inference problem, time varying model, and some inference problems around that. And then I will talk about a Bayesian time varying model. And then the second part will be about like more applied econometrics work, where we will talk about some of these forecasting models based on this, like, which are built around the GARCH model. So that will be most of the, like, that will be more or less our talk structure today. So this is, of course, different stocks that you are seeing. Of course, it's a question that it's very commonly asked, like, how can you predict, or can you at least say what is going on, what happened in the past? So if you see that for the first part of our talk, we will only talk about retrospective situations. So this is US dollar index. So US dollar index is like an average forex price. And here, as you can see, this is going up and down across, like, from the year 1967 to 2015. And what this picture shows is like certain peaks or certain dips were explained by certain external events. So this sort of, we will try to incorporate these questions by like a time varying model. So the first part, our initial goal will be to talk about models like ARCH and GARCH, but not with constant parameters, where the constant parameters would also evolve. Our motivation lies in pictures like this. I'll also show a couple more pictures like this, where you will see that this sort of data set is intrinsically non-stationary, and for such data, you cannot just assume that there is one single parameter value that can explain all these dynamics. So, so that will be more or less the structure, as I was mentioning. Starting for the time varying model, again, another picture. This is a real data, Bitcoin data in the year 2017, when it went from $100 to $20,000. So of course, there's a huge increase that happened, and it is probably very naive to explain this using single parameter. And this was one prediction, like around 2017. It actually went past both these numbers, which is kind of was unbelievable at that time. So this was due to some sort of forecasting model. So it's probably important to understand why these sort of models are working, what sort of models are like driving this sort of forecast. So this is the inception. This Robert Engel, he introduced ARCH back in 1982. It was a paper in Econometrica, and the model is as simple as this. YT is epsilon t h t power half, and ht is the conditional variance based on the past values, which is alpha 0 plus alpha 1 by t minus 1 squared. So this is a simple ARCH-1 model. It could, of course, be generalized by including more number of parameters. So this is Robert Angel receiving his Nobel Prize in economics back in 2003. And so this model is probably, so I probably don't need to sell this model enough. I don't have to do it, because if he has gotten a Nobel Prize after inventing this, it probably tells how important this model has been in the area of econometrics. So we will go a little bit deep into this model. I'll explain a little bit of this model, and then how you can generalize some of these components, how a natural GARCH component could arise from this. Now, note that like I wrote the same model replacing the t by I denotes the time, and yi is square root of alpha 0 plus alpha 1 by I minus 1 square times epsilon I. Now, in this model, how it differs from standard ARMA type of models is that it does not have a linear form. Like it is not yi is some past yi minus 1 plus epsilon I. There is this multiplicative form which makes kind of estimation a little bit difficult. Now, sometimes I must say that people do think that a conditional heteroscedastic model itself is a time varying model, because the volatility itself depends on past values. And of course, as you go on, your yi minus 1 is going to change, and thus you will probably get different values. So for this talk, we will not do that. We will still call this a time constant ARCH model. I will just touch base on like what we mean by a time varying model here. Now, even before time varying model, this estimation for ARCH model is not very, I mean, it's not an easy problem because of non-linearity. It's not an easy problem. So Arup Bose and Kanchan Mukherjee, they had a paper in 2003 where they cleverly wrote this yi square in like this. So as you can see, yi square becomes like an autoregressive model of order 1. And this has mean 0 if epsilon I squares are scaled down to have variance 1. So then you can think about this as an AR1 for yi squared. So they designed like a two-step estimation problem to estimate this alpha 0 and alpha 1. Now, this becomes a little bit more complicated. Like this technique will probably not work if your sigma I square becomes a little bit more involved, which leads us to this model GARCH. This GARCH model was invented around 1986, and it was by a student, PhD student of Robert Angel, Boller-Slave, and around that time, this model became popular. And as you can see, last time sigma I square was just alpha 0 plus alpha 1 by I minus 1 square. But now we have added additional component beta 1, which takes the past value of sigma I minus 1 square. And so this sort of model, of course, as you can recall, like as you can probably recognize, this has like an ARMA type of structure, but on the variance itself. Now, for this GARCH model, probably this two-stage estimation will not work. And thus we need like theories for how to estimate this problem. And then of course, we will do much more by generalizing these coefficients. So this is a brief history. Like ARCH was invented around 1982. GARCH was invented around 1986. Since the inception of GARCH, small order GARCH model like GARCH-1, which is like takes one past value of the yi square and one past value of the sigma I minus 1 square, is known to model many of this sort of financial data, especially log return data, pretty well. And then since its popularity, there were quite a few variants that were proposed, like AP-ARCH, GJR-GARCH, thresholded GARCH, exponential GARCH, ARMA-GARCH, etc., etc. So these sort of, I mean, this is probably a small collection. There are more than this. And usually, since the definition itself has a conditional variance part involved, so instead of writing the joint likelihood as product of individual independent component, we usually do a quasi-maximum likelihood estimation. That is, we instead maximize the summation of the likelihood of xi given xi minus 1. Now, this is not a huge problem because you can write the joint likelihood and then you can break it down by doing the conditional. It still comes out the same. And we will see that these data sets will have mean zeros when you take the log return, and it will show a lot of spikes, and it will show some heavy correlation when the data is squared. And specifically, it shows the heavy correlation when the data is squared because of the model, because of this earlier model, this yi square equals this. So this also is used to identify like if there is an like conditional heteroscedastic effect. So you do a square of the log returns, and then you plot an ACF function to see whether you can see significant correlation that is indicative of a conditional heteroscedastic model. Now, going into time varying model, we wanted to say that, like, of course, you can feed ARCH-GARCH model even just for constant model, like the models are not very easily algebraically amenable. So what we want to do is, like, of course, we have quite a bit of theory, like how to estimate this. For this part, we will talk about estimation of this model for the time varying aspect. Now, what exactly is a time varying model? So note that this is a paper from Equation Studies. They are pretty famous names in the area of econometrics. So they were looking at the SP500 data, and they were trying to feed the GARCH-11 model. And as you can see, like since the data set was varying, this was a 35 years of 35 years of data. So they were trying to plot alpha 0, like alpha 1 plus beta 1. And so they are in their computation, you can see the variant, like the variability, like it was changing quite a bit. The estimated values were changing quite a bit. So they were taking like a moving window estimates, and the estimate values were not really smoothly changing. And this probably tells that like it is very difficult to encapsulate everything in single parameters. So then what you can think about, like, okay, we can probably keep on including more number of data points. So here, this is the same data, but the re-estimates are based on the data point from 1 to t. And as you can see, like, of course, initially it had some variability, but it slowly decreased because you are increasing the number of data points to train your parameters. So it had lower and lower variability, and it also showed. But this sort of time varying estimate is also kind of not okay, given that for the entire time spectrum, the degree of reliability would probably vary, given that you are using different number of time points to estimate this. So this brings us to now the formulation, and then we will formally define our estimator. The formulation for a time varying ARCH model is, as we have seen the ARCH-1 model, initially there were just constants alpha 0 and alpha 1. Instead, we replace them by alpha 0 of I over n and alpha 1 of I over n. And this constitutes a time varying ARCH-1 model. If you are trying to do time varying ARCH-P model, you would have alpha 0, alpha 1 up to alpha p. And if you do a GARCH model, there would be additional sigma I minus 1 square problem, like sigma I minus 1 square here. But the main reason I put this slide is to show the parallel between alpha 0, like the constant model, and the time varying ARCH model. Now, what is exactly a time varying model? And I mean, this slide actually shows how easily you can transform your time constant estimation framework to a time varying estimation framework. So a time constant model, like standard models, these models are not, of course, the ARCH-GARCH models as such, but these two models are simple models that I am using here to illustrate how you can transfer a problem from time constant estimation to a time varying estimation. Now, the time constant model, let's say you have a trend, a simple trend G plus EI, which is a singular number. Of course, this is not realistic, but I'm just saying for illustration purpose, assume that there is a single number G or a single vector beta, or like single parameter values alpha A0 and A1 that can give us these models. These are time constant models. Now, moving from time constant models, we are now generalizing the G, now generalizing the beta, and now generalizing the A0 and A1 to instead like functions ranging in 0 to 1. And it can also have like other distributions, like it can also tap into like a more generalized linear model framework, where instead of having this sort of mu and a values, you can replace the mu and a by corresponding functions. So our first part of the talk will be focused on this sort of time varying function and how to estimate them and build valid inference. Now, first of all, what is the goal of doing inference? By inference are of different types. One question that we will do here, like we will deal with the simultaneous confidence band. The first question is, why do we even care about simultaneous confidence band? Where easily you can do point-wise confidence band, you can look at this sort of estimate of the functions, and then you can just say, okay, we can estimate these numbers, we can have a estimate of the sort of the standard deviation of standard error of these estimates, and that's it. But if you're trying to talk about the entire range of the function, one of the important questions that people usually want to ask is that whether the parameter value was more or less constant or whether it was changing. So simultaneous confidence band allows us to answer this question. So what we will do is we will estimate the function, we will create curves around that. And once we do that, then we will try to see whether we can fit like a horizontal line inside those curves. And now, if you are trying to talk about the entire range, then you need to go to do a simultaneous confidence band. A pointwise confidence band is just not sufficient. Once you do a simultaneous confidence band and you do see that you can fit a line here, then maybe you can refit your data using just one parameter value. Now, it could so happen that your confidence bands might show like, okay, you cannot fit a horizontal line, but maybe you can fit like a linear line, or maybe you can fit like a quadratic line. Then you can re-estimate all this using like a more now you have some evidence from the data that your trends are going to be like that, and then you can sort of reduce your data like parameter burden to a single or couple of parameters. So these are the data sets that we will explain later, but this is USD GBP data set, and like we have shown that for the intercept value, the alpha 0 value, you cannot actually get a horizontal line. However, for the alpha 1 value, it's probably okay to still fit like a single horizontal line, since the two curves end up containing a horizontal line inside them. Now, how do you generally deal with an estimation for a time varying model? Like time constant model itself, we are doing it via the quasi MLE. So how do you generalize this to a time constant model? So again, we fall back upon how we do this for simple model like this. So if you were given a yi equals g plus epsilon I model, if g were constant, which was the first time constant model I was showing, how would you estimate that number g? Probably in some form of least square estimate, you will do this, which will also be the kind of like a maximum likelihood estimation under normality assumption. Now, instead, if your theta is varying, if your g is varying, you cannot just do that. And we take like a kernel-based approach to estimate this theta at every point t by adding a suitable weight function, which varies at every I. Now, this leads to the famous Nadaraya-Watson estimator, which is, of course, kind of equivalent to an estimator like a Priestley-Chow estimator. So you can see clearly this one is close to what your estimate would be if this was a constant, except for the fact that now you have an additional k factor here. Now, why do I have this slide here? Of course, this is not new. This is nothing novel. But the idea is that for simple models like this, it's very easy to put a kernel here, and instead of getting the simple average, now you are getting a weighted average. So that is another Watson estimator, which is kind of equivalent to the Priestley-Chow estimator. But when your models are not easily estimable, you cannot have a closed form solution for theta hat. But no matter what, you can still define your time varying estimate through a kernelized weight function like this. So that's what we are going to do. So if you have like a time varying regression problem, you do the same thing, but again, for this problem also, you have a very simple solution. You can just replace the like yi minus xi prime theta whole square, and you can add like a weight that will give you a theta hat t. Now, time varying models actually came into the fore around 1990, and it became very popular because of this time varying regression problem, especially in the area of economics, because people were trying to extract important covariate effects. And to build confidence interval, there were a few works in terms of how you can do inference from this sort of time varying models. And the good thing about time varying component for regression setup is that theta hat t minus theta t, you can very easily show that it's a weighted average of xi times epsilon I. And this means that this has a mean 0. So you can easily do some sort of like a CLT type of invariance principle result, and that will allow you to get a simultaneous control on theta hat t minus theta t. But the same technique will probably work for time varying AR type models as well. Like if you have a linear structure, it will probably still work, and you can still simply have a closed form solution. But if you do not have a linear structure, this sort of easy estimation is killed out. I mean, you cannot just simply say that. And then we have to build a sort of more general framework that is based on a quasi-maximum likelihood estimation. Now, this is where our contribution starts. Like multiple references have already pointed out that we need to make the inference specific to this sort of ARCH-GARCH model, and it was not there. And like point-wise inference was there, maybe just a couple of papers, and we wanted to extend this to simultaneous inference. Now, this is where we thought like, okay, since we are doing a more general framework, maybe we can put it out for a very general class of models, and like that allowed us to build a general framework for time varying time series model, where we could do this sort of estimation for a very general class like this. In particular, this class also covers like an ARMA-GARCH type of models like this, where your sigma part will cover the past values of the yi square and sigma I square based on whether it's TV-ARCH or TV-GARCH. Now, how do you estimate this? Again, the idea is not too difficult. The idea is to add a kernelized weight, and instead of that yi minus theta I square, this time we will be doing a yi over alpha 0 plus alpha 1 yi minus 1 square. We in fact were able to do a local linear estimation rather than just local constant estimation, but I will not go into the details of that. So you can just omit this theta prime part, and you can just estimate L of ZIC and theta to estimate the values of theta hat t. Once you estimate the values of theta hat t, we will show that theta hat t minus theta t can be individually controlled, can be simultaneously controlled. So there are certain assumptions. So for the sake of time, we will not go into the details of the theoretical results. They are all in the paper, so you can have a look. And if you have questions, I'll be happy to answer later. We showed that, okay, that our estimators theta hat t by this means are consistent, and it has a simple normal convergence, like it has asymptotic normality. But note that this is like a point-wise result. This will not allow us to build a simultaneous confidence band, which is needed to talk about whether we can reject or accept the time constancy of the parameters. Now, again, this is a theoretical sort of nugget where I would not spend a lot of time, but our main trick was based on a Bahadur representation, where we showed that uniformly you can control theta hat minus theta by a means of a Gaussian approximation. Instead, I will probably prefer to show a picture, and that picture will allow us to show why we can get a nice theoretical result like this. So a theoretical result is here, which is a Gumbel convergence. A Gumbel convergence is there, like it's kind of well known that there is a Gumbel convergence for extreme values of Gaussian processes. So what we intuitively do is that we write theta hat minus theta in terms of sum of some mean zero random variables, as we are trying to mimic what we know for time varying regression. And based on those mean zero random variable, we are trying to get Gaussian approximation. And once I have the approximating Gaussian process, I can use some extreme value results for Gaussian process to get to a Gumbel convergence. Now, Gumbel convergence are well known to suffer from logarithmic scales, meaning that unless you have a huge data set, you will not be able to get to the correct coverages. So for that reason, we are proposing a bootstrap technique. And this bootstrap technique is also based on the Gaussian approximation that we are doing. So maybe like getting rid of like all the theoretical details, I will just conclude this part by showing like a sort of an pictorial illustration of what we are trying to do. This is my model, this is my data sets, and say this is a true function curve that we are trying to estimate. We will start with our initial estimate. And once we start with our initial estimate, we will show that this initial estimate is close to theta t by a factor like this. Whatever is our approximating error, we replace those HIs by GIs so that we can create a Gaussian analog of our estimate. And once I create the Gaussian analog of our estimate, I can keep on generating these black lines. This black line will be based on, as I'm mentioning, this is a Gaussian estimate. So based on how, like in each iteration, we will keep getting different black lines. This is kind of like a bootstrap technique. And once I keep getting these black lines, many of these black lines, I can create like a band like this. And that band will probably cover that band, like as I can show in this picture, that band is covering the true function. So we can easily take this one as our maybe 95% confidence interval. So this is plotted for 95% confidence interval. The idea is we want to capture this blue line, start with the red line, get a Gaussian analog by this black line using a bootstrap procedure, and then we keep creating copies of that. Now, we did some simulation and we showed that our results were showing good results for 1,000, 2,000, and 5,000. In our JOE paper, actually, we have it for 500 as well. So if you're interested, you can go and check that. And we are, of course, going a little bit below 90% and 95%, but that's kind of normal for ARCH-GARCH models. And if you're questioning, sometimes I get this question, like, why are you doing this for such a large sample size? What happens for 100 and 200? It's very rare to have like good results for this sort of ARCH-GARCH models when you have only a sample size of 100 points. We will talk about that in the Bayesian part where we will address this issue more severely. Like for the real data analysis, as I was mentioning, we will look at the log return data. Now the log return data is like a mean zero data and it's close to the relative returns for every day. And typically this log return data is what we analyze for this ARCH-GARCH model. These are like mean zero, almost mean zero data. And we will try to show analysis of this NASDAQ 2011 to 18 data. As you can see, when I square the data, it does show significant correlation. And typically, as I mentioned, lower order GARCH are used. So as you can see, like all these three curves, this is probably showing a linear pattern, but this is more or less, these two are more or less showing kind of, I mean, you can probably fit like a horizontal line, except for the point around the end of it, it dipped below, where you cannot fit any line. So probably this one needs like sort of a thresholded type of parameters if you want to sort of go for a more objective estimation. But here you can see like these are more general. You can just keep it like this, and we showed in our paper that our time varying estimates are also good in terms of forecasting. So these time varying estimates are fine. You do not necessarily need to bring it down to single parameters. Now, in this paper, like we were talking about some sort of estimation problem, and like we build the inference, but we needed a strong condition that this beta 1 plus root 3 alpha 1 has to be less than 1. Now, and this has to happen uniformly across T. Now, this is a very difficult constraint that we had. And I must say that like for real life data, if you feed alpha 1 and beta 1, I showed that initial bulky image, and like you can see that alpha 1 plus beta 1 was frequently going up above 1. So if you put a condition like beta 1 plus square root 3 alpha 1 less than 1, that becomes very stringent. But also alpha 1 plus beta 1 equals 1 is a difficult condition. And for most of the data sets we were trying, it was actually coming out close to that. But of course, after some search, we were able to find this. And this actually builds some motivation of like for our next talk, where we will, for our next part, where we will do like a Bayesian estimation for this problem. So these are some of the references, and these references, this is the main paper, the ARCH-GARCH estimation paper, and this second paper constructs a Gaussian approximation that creates a backbone by providing a simultaneous inference. Now, for a Bayesian estimation, as I mentioned, the first major motivation was if we can do some sort of estimation for small sample sizes, and a Bayesian estimation probably can be helpful. And instead of course, it's very difficult to do simultaneous bands, we will instead do a Hamiltonian Monte Carlo based posterior sampling criteria. And we were able to establish posterior contraction. Now, posterior contraction for such dependent time series was something new. And initially we started with a Poisson count model, a Poisson count time series. And very funnily, like Poisson count, if you're familiar with Poisson count random variable, there's a model called IN-GARCH model. Now, from this name, initially we were just trying to do this Bayesian modeling for count time series. But since that name has IN-GARCH, and I have been working on ARCH and GARCH for a while at that time, I thought, why don't we try a Bayesian GARCH type of model? And that led to this piece of work where we worked on ARCH-GARCH and model. And not only that, as I mentioned that this A plus B has a tendency of reaching 1, These sort of models are called integrated GARCH or ARCH model, and we were able to handle this ARCH model in this Bayesian framework, which was not there for which we could not do, of course, for the frequentist framework. And the model again remains the same. The model does not change. This is a GARCH PQ model based on the past values, and we have the same sort of parameter restriction. For the GARCH model, we have, of course, a restriction that summation of these coefficients are less than 1, but when we will go to iGARCH, we will relax this assumption. So this is a prior modeling where we use like a B-spline based method, and we used a Hamiltonian Monte Carlo to simulate this data, to simulate this, to simulate and like from the posterior. And once we have the posterior, we can create these confidence intervals. And so we obtained a theoretical contraction rate for this posterior contraction, meaning that the posteriors will be able to get to the true value based on a certain distance square. I will not go into the details of this. These details are based on some of the works by Shubhashish Ghoshal. Like he has been working on doing this consistent test statistic. Based on that, we were able to achieve an optimal posterior contraction rate. I will just show some data sets where you can see, of course, when you have n equals 200, our estimations were not that great, but with n equals 500, we were getting close, and with n equals 1000, we were probably doing pretty good in terms of the credible interval was covering the entirety of the spectrums of these curves. Like I must mention, even for small sample values, it's an extremely difficult problem in ARCH-GARCH, and people typically only use sample sizes above 1000. So in this work, we were a little bit bold and ambitious. We wanted to try it for small values as well. And we could show that our base TV GARCH was able to beat the existing like simple GARCH model, and even the TV GARCH model that we initially proposed in this earlier work. We were able to beat both of them. Not by a huge margin, but at least there was some gain. And in fact, you can see like even for frequentist TV GARCH, we were not able to beat just the simple GARCH by a huge margin as such, but the Bayesian TV GARCH for small sample showed some significant advantage. So we also analyzed the real data, the same data that we analyzed for the frequentist framework, and we got curves like this. Note that this sort of curves, the credible intervals, these are not this does not have the simultaneous coverage guarantees that the earlier papers had. Now I want to talk a little bit about this ARCH model before going into the forecasting part. This is something that was a good contribution for the Bayesian part, because it was very difficult to deal with ARCH models, because ARCH models, whenever you put alpha plus beta equals 1, it becomes intrinsically non-stationary, and that makes the frequentist framework completely fall down. But for the Bayesian framework, we were able to get it through. And then here we can show that like these ARCH models were kind of more appropriate for a number of data sets. Like we kept the data set in NASDAQ data, and we showed like we were able to get better coverage rates by this ARCH model. So there was definitely a motivation to do some TV like time varying ARCH model, and we were able to do it via the same sort of thing. We use the B value as 1 minus alpha 1. We reparameterized everything in terms of just the alpha, and we were able to reduce some of this estimation. Like we were able to also handle this ARCH model here. So the Bayesian work kind of contributed in reducing the GARCH moment assumption to only 2. Earlier it was 4 in that earlier like frequentist paper. And of course, another contribution was we were able to handle TVI GARCH model. We showed reasonable coverage and good forecasting performances around the small sample size value of n equals 200 and 500. So we were also thinking like for the future work, we're trying to get some other stochastic volatility model. And for each of these models, somehow the prior modeling has to be kind of different. So we will probably we are working on something like this, and we'll probably be able to publish something on this line. So the two papers that came out here, this is the first one is the Bayesian ARCH-GARCH model. And this was motivated from an earlier work, which was from a Poisson count time series model. Both these have the same, the Hamiltonian Monte Carlo type of estimation technique. but the mathematics for these two are a little bit different based on the model structure. Now, finally, in the last part, I will try to conclude this in maybe 6 or 7 minutes. I will talk a little bit about forecasting. So this was another focus of when I was doing my PhD, is like, how would you forecast? And in fact, for the econometrics world, people do get more interested in forecasting instead of just estimating. Even when we send this paper, we got review questions like the earlier paper about simultaneous inference. We got questions about, we understand that you are trying to talk about the retrospective, you're getting good estimates, but what can you say about the forecast? Can your model still do a good forecasting? Now, we of course had to say this, that like, so for time varying models, it's very difficult to use those forecasts, like you use it for the future forecasting, because time varying model intrinsically is tied to past values. You cannot estimate a function for the future. So that's why what we did was we thought like, we of course broke it down into small rectangular kernel, like small rectangular windows, and then we were using those estimates to get the next few values. So for the forecasting part, I will just talk a little bit about like aggregated forecasting. So instead of forecasting just one single value, like observing x1, x2, xn, instead of forecasting just say xn plus 10, we are more interested in like forecasting the aggregated value of the next m values. Now, this sort of forecasts have been kind of common in the econometric world. Rather than just single value, it does not hold a lot of meaningful interpretation, because you would probably want to see, say if these are log returns, you would probably want to see in the next 30 days whether overall your log return summation is going to be positive, meaning whether overall you will be making some money or not. If you are a if you're a service provider, you probably want to know what happens to your demand for the next 30 days, so that you can probably set a strategical price like based on that. So we were doing some simple linear model, like some simple linear structure model, where we were proposing some techniques of doing a quantile based estimation on this. These were in this paper, but these were not GARCH specific. And the typical idea was to use somehow estimate these quantiles of this. And since this is like an m block sum, the typical idea was to get the residual values from the past and then look at this. Now, for this sort of the challenges here for GARCH model is that you cannot really necessarily just do this, because if you have a simple linear model as yi as some xi prime beta plus ei, which was, by the way, this work, you can easily get the residual values. And once you get the residual values, you can create like quantile based estimation or like a prediction of this residual part. You can put back the xi prime beta hat very easily. You cannot probably do the same for a complicated model like GARCH. So here for this part, this is a work with a student, graduate student. So he's doing his PhD with Professor Politis. So Professor Politis introduced resampling bootstrap around 1994. So he has been working on many different bootstrap models. So we wanted to sort of take this idea and we wanted to extend this to some sort of GARCH-based modeling. So we did like a model-free forecasting where you do not assume like the normality assumption on this. So based on the GARCH model, you would invert this and you will try to create many copies of the W values from the estimated residual values. Once you do that, then you can create like future forecasts like yn plus 1, yn plus 2, yn plus 3 based on that. And this is again called model free, but technically it should probably be distributional assumption free. That's what it is, because I mean, even though it's called model free, it's based on like a specific ARCH or GARCH model. So what you will do is you will, again, like I showed the inverse function, you will try to get to the error part, by inverting this based on this. So what we can do is we can estimate the A0 and A1 by some time varying thing, like by some time varying estimate, or you can just use the simple A0 and A1 like a time constant estimate. You can also do a grid search, which was initially what Politis has done. And you can try to generate these residual values, WT, based on the past value. So you can get the WT hat, W1 hat up to WN hat. And based on W1 hat and WN hat, you can then construct the formula for yn plus 1, yn plus 2, yn plus 3, and so on. So you can keep resampling these wy's. Given you know that these wy's or the epsilon i's or the innovations are independent, you can keep resampling it from their estimated residuals, and you can keep putting it back to get to the value of yn plus 1, yn plus 2, yn plus 3, and so on. And then you can create like sort of, you can take the median value or take the mean value, and then you have a forecast for yn plus 1, yn plus 2, and so on. And then you can sum them up to get to the final value or final forecast value or forecasting value of the yn plus 1 to yn plus m. So this is what I have explained here, that yt plus 1 can be written as a function of wt plus 1, but we do not know wt plus 1. But for that, what we will do is we will estimate wt plus 1 based on the past values of wt. So these are some of the details. These are like this was initially proposed for an ARCH model, like an ARCH infinity model, ARCH-P model. We generalized this to a GARCH structure, which had lesser number of parameters instead of like P plus 1. So it was easier to estimate, and we showed that our like GA novus. So this sort of methods are called also novus method, because you are doing a variance stabilizing transformation, this YT by this thing. So we called it GA novus, and GA novus, another variant, we removed the A0 part, and we were able to show that our method GE novus without A0 and GA novus without A0 were able to get significant forecasting boost based on the simple GARCH model. And we also showed that when the number of steps were increasing, our benefits were increasing. Like we were seeing more significant improvement based on these GARCH models. So we allowed so the natural question is, how are you comparing two forecasts? So we were using Diebold and Mariano test, and we were also using Clark and West test when we have multiple steps. Like this Clark and West test, Diebold and Mariano test, this is a JOE paper from 1995. They compare two forecasts, two different forecasts. But if the forecasts are nested with each other, we should use like a Clark and West test, which kind of gives you some sort of, which accounts for nested model. And it, of course, if you introduce one more parameter in your model, you will see lower forecast, but it adjusts for that. So it gives like a true competitive advantage. It will spit out like a true competitive advantage if one of the method is better than the other. So this CW test allowed us to test some of this forecasting model to see which one is doing good. And the basic summary of our work here is that novus type method did outperform the GARCH-11 methods. And these new methods that we proposed, we proposed 3 different variants in 2 papers, and our new methods significantly beat this GE novus method. And the victory of new methods can sustain against statistical tests such as CW test. So when I was showing that long table, we were just showing the MSE values, but we also showed that by the means of CW test, our new methods were significantly improved. And finally, I will just use just one last minute to talk about 2 other GARCH-based application work. These are works with work in the area of econometrics. These are mostly based on the sort of GARCH models with different covariates. Now, GARCH-X models have been around. There has been like a theoretical guarantee paper in this paper in 2019, where if you introduce another covariate in this GARCH modeling, you can systematically estimate this. And their theory was also able to handle the more general AP ARCH model. Now, this GARCH-X package in R actually helps in estimation, but it has some problems. This we are trying to sort of see if we can sort of remove those limitations. But I was not aware of this. Like recently, I got to know that like other GARCH packages like RU-GARCH, F-GARCH, they also allow external covariates. But this one does a quasi-MLE estimation, but those 2 were allowing like just a least square estimator. Now, in this paper, a recent paper came out where we were looking at the Bitcoin's network daily electricity load as our covariates. We were looking at daily spot price data, which as the log return data of the daily spot price in 3 very prominent electricity market in US. And we showed that this volatility effect was increasing over time. and these covariates have, like, the impact of these covariates were increasing over time. So what we did was we took the GARCH model and then we fit a time varying GARCH model for this. So we proposed like a time varying analog of this, and we showed like a time varying GARCH model shows this result. And we have another paper where we talk about long-term forecasting. This did not come out yet. It is submitted earlier this year, where we were looking at the gold return values and its volatility. And we were trying to see if the volatilities can be Yeah, sorry, I think I got muted, so that's okay. Let me go back to this. So we showed that the bubble indicators, I mean, so interestingly for this one, we had a high dimensional, like many number of covariates, like there were many bubble indicators. So 42 predictors for G7 countries and all the BRICS countries, and 72 predictors for just the G7 countries. And so this was like a high dimensional regression setup. So interestingly, in this one, we first estimated the volatilities instead of estimating the volatility with the covariates. And with using these targeted GARCH volatilities, we bring in the bubble indicators in a high dimensional regression setup. And then we allowed like our JTSA technique to estimate the future forecasts. We showed that the bubble indicators allowed us to get good significant forecasts, like small p values for the two ranges. Like when you were training based on the past 100 data or past 250 data, we kind of showed small p values, which means that our bubble indicators, particularly when both positive and negative bubbles were combined, can accurately forecast gold return data at short or medium term, and the time varying estimates of gold returns volatility. So the return data I did not show, I just showed that gold return volatility, since this talk is sort of targeted towards ARCH and GARCH. I just wanted to show that this estimated volatilities can also be explained through this bubble indicators. So that kind of brings an end to what I wanted to talk. I know there's a lot of things that I went over. The last part of this talk, there are a few references I want to point out. The multiple forecasting technique was proposed in this paper, like forecasting for aggregated horizon. The technique was here. Then we showed some theoretical guarantees for this under the high dimensional regression setup with the graduate student. This was one work that came out last year for this GA-Novus method. For this one, so this was just the GE-Novus method. So we proposed a small variant of the GE-Novus. And for the GE-Novus, this is a longer paper. This is now going through revision. And then the Bitcoin paper is here. And then finally, this is a submitted work, but it's available in my webpage if you have questions. So sorry about covering so many things here. So maybe we'll have questions. I can take questions now.
Thank you very much, Sayar. So we have maybe one or couple of minutes for inviting questions. From the audience, if there is any question or remark, please mention.
Yes, I have a few questions actually.
Sure, Yuan. Yeah, good to hear from you.
Yeah, so thank you. A nice talk. Time varying GARCH. I have a few questions actually. A couple of questions related to the theory, and also a couple of questions related to the forecasting. So related to the theory, I have actually a paper, from my PhD called locally parametric estimation in high frequency data, where I assume that there is a time varying parameter which follows in general a semi-martingale. And in particular, I show central limit theory for the a kind of time varying MA1 model. So it's not included in your setup, but in my setup, I have infill asymptotics. And as I understand your setup, this is, you have the T which goes to infinity.
Right.
And then how does it goes? I'm not sure about your asymptotics actually.
Yeah, so that's a good question. So I think, I mean, in our model also we have, we also call this infinite asymptotics in the sense that, let me see which one would be the good.
Yeah, thank you.
Yeah, so maybe I can explain it with this one. Yeah, so
Okay.
typically you can probably use θ1i, θpi, and you can assume that this I is going to infinity. Instead, what we are doing is we are rescaling everything to the range 0 to 1. So the idea is this, that if you have more number of data points, you will be able to recover more local structures of these functions, because then you will have information on a denser set of points in 0 to 1. So we are also doing kind of an infield asymptotics. I probably don't know what type of infield asymptotics you are talking about, but we also call this like infield asymptotics as such. So our n goes to infinity, but we have this I over n. So typically what we assume is that there is a background locally stationary process that can kind of that can approximate this process. So there is another process, θ1u plus θpu, fixing at every u, so that this yi based on the u process and yi based on this process are close to each other. So that is kind of a basic ingredient how we can do this sort of theory.
So in that case, it's really, it's really related to my paper. So I will just send you the link.
Sure. I think I have read your paper long back. I have, but what you were probably doing, you were assuming these coefficients as random variables or fixed.
No, just it's the same as you. Like this is between 0 and 1. Okay. Yeah, this is same as infill asymptotics, but this is semi-martingale. So I was just able. I have many examples, but I was just able to use an MA1. So in any case, it's the results are different. So, you know, it doesn't overlap with your contribution. I just wanted to make sure that. And then I have questions on forecasting. Is what are you forecasting? Are we talking about volatility or like
Yeah, I think I had to rush a little bit on there, but maybe yes. So typically you can have like you can, this could be log return, this could be volatility, both of it. Like it's not a problem, like if it's volatility or if it is log return itself.
Okay.
So this paper, these two were done based on like the general time series, but of course mainly the main ingredient is based on like a mean zero forecast. So what we do is we subtract like the xi prime beta part, and when we subtract the xi prime beta part, we are at the residuals, and then using the residuals we do the forecasting, then we put back the previous estimate. So that's what we are doing. But for this work, like for the G innovus and G innovus, we are forecasting the YT square. We are forecasting YT square. And so typical, I mean, you would not be like, you can forecast, you can say that that's an good estimate of the sigma t square. So here we are looking at yn plus 1 square, yn plus 2 square, and so on, and seeing whether our forecasts are going close to that. That's what we are forecasting for this piece of work, G innovus and G innovus.
All right. Yeah. Okay. Thank you very much. Yeah, this was really nice talk. Thank you.
Thank you, Yuan. Thank you. Let's talk more afterwards.
Yeah. I'll let you know. Yeah.
Sure. Thanks, Yuan.
Okay. Thank you, Sayar, for this talk, excellent talk, and also the question and answer this session. Is there any question from the audience? If no, then I thank you again.